So first of all, why displacement current? Why it appeared in Maxwell equations? So going to the Ampere's law, where JF is a current density of the free charges, and then the continuity equation. Continuity equation tells that all charge is conserved. We can plug this in the continuity equation and see that we get divergence of the curl of magnetic field equal to partial derivative, which is wrong because the divergence of the curl is always 0. Then to fix this problem, Maxwell introduced one more term in the Ampere's law, which is displacement field and displacement current. There is important term, the divergence of the displacement field is on the free charges. So then if the divergence of the curl, as it should be 0 of magnetic field, H, then again we plug now this in. Zero, what else can we do? We can open the brackets. Okay. Here's, this can be plugged in. Now, if we take this partial time derivative out of the brackets, this part can be plugged in this. Now we can take the divergence again out of the bracket and bring this in. So that the divergence of this part is 0, this part must be equal to this. So that's equation for the current density, displacement current density, which is also time varying electric field multiplied by these epsilons, which are responsible for the properties of the material in which the displacement current is going through. So that was it, a small introduction about displacement current and Maxwell equations. Then all Maxwell equations can be written in the following form. So now going back to the problem of capacitor. There is given a parallel plate capacitor with two circular plates with some S area, and between them is a vacuum. And this capacitor is connected to the battery, giving the constant voltage. The plates are slowly oscillating so that they remain parallel, but the separation between them, D, is time varying. It needs to find the magnetic field magnetic field H, between the plates produced by the displacement currents. So using this equation, we can find the H magnetic field. So for this circuit, where the capacitor has a circular plate of area S, and the current flowing in this way, the displacement field between the plates is directed in this way along z-axis. So let's try to solve this problem. To find H, we need to find, so between the capacitor plates there is no flowing electric field, no flowing free charges current density. There is no flowing currents here beside the displacement field and displacement current. So we need to find this part. So this is 0, and we need to find the displacement field, which we can find from electric field. So when capacitor is charging, the charges are accumulated on these plates in the way that charge density is charge per area S of the plate. And then electric field here before the plate is equal to epsilon naught U divided by epsilon naught S in that direction. And the displacement field is equal epsilon naught epsilon r times electric field. Epsilon r, the relative epsilon is depending on the property of the material. In this case, between the capacitor plate is a vacuum, and vacuum value of epsilon is 1. So it's and this is the value for the displacement field between the capacitor plates. Now we are not knowing the Q, but we can describe Q through the voltage. We know that in the circuit is flowing constant voltage V, constant voltage V. So V can be found as a difference of potential from electric field. It was already shown in the previous problem how it can be found, and it's equal to capacitance divided, charge divided by the capacitance of the plate. And we add here term S. And here we get the displacement field. Here's our S, and capacitance is epsilon R D S divided by D. So then we can write the displacement field. Divided by the distance between the capacitor plates. Seems to be correct, and here actually, if I'm mistaken, it's there is a magnitude of D. So D in the Z direction, and if I want to write it in, as a vector, it's in Z direction. So voltage in the circuit, this epsilon R is equal to 1, and divided by the separation distance between the capacitor plates. So now we can plug this. We can plug this in here, but first we need a time derivative for this thing. And we know that the time changing time changing parameter is the distance between, is a D. Then writing the time derivative from this formula is so D, the distance between, is given as follows. D squared times 2, minus 2, and then there's omega, and then cosine omega t times d1. Yeah, that seems to be like that in that direction. So going back to the equation for the H field is equal to in time displacement field between the capacitor plates, and then if we integrate it over the area, here we can rewrite it using Stokes' theorem. So H will be along some line, and the displacement field is still through between the plates, so it's normal to the surface. And finally, let's write this side. So here we just get the area. Normal is Z as well. Okay. So here is -1 cosine negative times area S, and direction is gun because of normal and here. Direction will come from this side, right? So what would be the direction H? H is rotating, and then it's cross product with perpendicular to displacement field. And what is important to notice that H is independent in translation direction, and H is independent in angular direction, but H is dependent on the radius of taking of this dl of the integration line. So for the circular, in the rotation, it will be along the circle, it will be 2 pi r, and then H is in phi direction as a B field. H is direction of H is found exactly the same like a B field. And then we have 2 pi r 2. And finally, can be written the H field. Okay, that's our answer. Let's see if it's correct. Well, the area of the circle going deeper is PR squared, and then pi can be cancelled and square can be cancelled, so then it's just instead of S here is R. But I also lost the minus. Here is a minus. And then minus is here. And the 2 actually. Yeah, okay. Mistaken. Here is no mistake. So then this 2 doesn't get cancelled, it goes for here. Yes. Good.